I am Keith Moffatt, Emeritus Professor of Mathematical Physics at the University of Cambridge and Fellow of Trinity College, Cambridge. Welcome to my exp. Fluid mechanics has a very important part to play in biology generally. There's a whole area described as biological fluid mechanics and also physiological fluid mechanics, which is concerned, for example, with airflow in the lungs or flow of blood through the blood system, the veins and arteries, the pumping action of the heart, and so on. So obviously very fundamental from that point of view, and something that we need to understand in attempts to combat disease. And going down even to the smaller scale, to the level of the human cell, at that scale, viscous forces become of dominant importance. Inertia becomes totally negligible. Surface tension effects can be very important as well. And some fascinating problems arise in that area. It's an area that has developed under the title microhydrodynamics or even nanohydrodynamics if one goes to extremely small scales. A lot of excitement in that general area over the last 20 years or so. But let me go back for a moment to the business of helicity. And there I should have mentioned that in the dynamo context, the conclusion really is that large-scale magnetic fields can arise out of small-scale turbulent activity. And it's a wonderful example of how order can emerge out of chaos. This helicity invariant that I mentioned was, in a sense, already recognized way back by Kelvin in the 1860s, who realized that what we describe as vortex lines or vortex tubes in a fluid, if they are knotted, then they remain knotted for all time. That's on the basis of the Euler equations. And he got very excited about this result. Now, it wasn't until, about 7 years ago that knotted vortices were realized experimentally for the first time in a laboratory by a team in Chicago. And this again led to great excitement in this area, the area of knotted vortices. You can also have magnetic field lines that are knotted. And the question there arises, can you ascribe an energy to a knot? And you can in a very natural way in the case of magnetic field, because a magnetic field has an energy. So a knotted magnetic flux tube has energy. And then the question is, suppose you allow that magnetic flux tube to relax to a minimum energy state. Well, what will it look like then? That has led, and curiously, it's led in the biological context that we started from here. It has led to the concept of tight knots, just like a tight knot in a shoelace, but a tight knot in a mathematical sense, which has an energy related to the particular knot that you're dealing with. There's been a lot of work on this area in, again, the last 20 years or so. And it's an area that I was involved in back in the 1990s through realizing that you could approach not energy through this magnetic context. Applied mathematicians, I stress applied, are motivated by the need to understand processes in nature, natural processes that we observe around us or out in space, or that are detected in the interior of the human body, for example, or observing, I'd say, things like the flight of insects or the flight of birds. Pure mathematicians are motivated more by the development, the understanding of abstract structures that have their own internal beauty, rather like abstract art. In that way, not accessible to everyone, alas. One does need a basic mathematical training to appreciate this sort of beauty. But one of the miracles is that these beautiful structures often come quite unexpectedly to play a part in the understanding of natural systems.